So now you are set up to look at some real life situations of all these basic concepts of large scale balances. Okay, so we had seen this, I've mentioned this several times. When you look at this zonal mean meridional section, you have warm lighter air sitting at the surface, and you have cold heavier air sitting at the surface as well. If this was a water tank, for example, and you tried to create such a situation, unless the tank is rotating, you cannot do that, right? Because if you just have warm water on top of warm water below heavier water, then you're going to have adjustments. So if this air is heavier, remember these density decreases as you go up in altitude, but here you are at the surface, so the pressure is higher as well. So temperature and cold pressure together make for heavier air here, but here you have colder air, but pressure is lower, so you have lighter air on top. But just looking horizontally, this air is lighter than this air, so this air can just rush in, but that doesn't happen. So in a tank, if you had heavier water here and lighter water here, the heavier water would rush in unless you had created some sort of a radial balance like we had been doing in the lab. We will do that again here. So we created this system again where we have the metal cylinder sticking above the water level. Here again a solid body rotation is established, and table is rotating pretty fast at 10 rpm, and the can is slowly filled carefully and slowly with heavier salt water that is dyed, so that you can see this adjustment that happens when you pull out the cylinder. So once the flow is steadily established, the can is pulled out very rapidly as to not disturb the flow. If you pull it slowly, then you will have heavier water flowing out from the middle. But if you pull it suddenly, then the balance has to happen with gravitational pull down and centrifugal force acting on in the radial direction. So this takes a lot of expertise, as the book tells you. So once the cylinder has been rapidly pulled and the circulation has been established, you have the sloping surfaces forming, deviating from the original R1 of the cylinder, going in by about delta R and going out by delta R. Okay, so if the tank was not rotating and you put heavy water in the middle and pulled it out, heavy water would sink to the bottom and spread out towards the edges, push out the lighter water up, right? But because the system is rotating, there is a cone created which should remind you like the cone we have here if we look on the sphere. If you look on the sphere, you have cold polar air forming a cone with the tropical warm air holding it up, right? So basically we have to look at the relation. Now you have created a front here between the lighter density and the heavier density, and there is a circulation happening that is parallel to the front as well. Okay, so the heavier water is moving at a slightly different velocity than the lighter water in the azimuthal direction parallel to the front. So long time ago in the 1920s, I think a relation was derived for that for the atmospheric fronts, and we'll look at that. So here is how it is done. Here you have the setup. The tank is rotating, it's equilibrated, and then you boom pull it out, and you can see that the tendency for the heavier air to collapse and blow out starts, but the rotational effects constrain it. So here it's in the side view, you can see the tank is rotating this way, the front is created this way, and you have a flow that is going into the page here. So we're looking at the tail of the arrow, and it's coming out of the page at us here, looking at the head of the arrow, right? And there is the front. Okay, so there are horizontal swirling currents. What does this remind you of? This is our kind of jet stream that's cruising along at the top, right? So that's kind of the referee of the wrestling between warm tropical subtropical air and the cold polar air. We will see that there are multiple jet streams, and the outer one, the polar jet stream, is the one that we worry about most. Okay, so let's derive the equations of the Margules relation, the so-called Margules relation, which relates the slope of the front gamma to the density difference and the velocity differences. So we are still holding on to hydrostatic balance to start with, but the front also has to have same pressure whether you come from this side or this side, right? Because pressure along this line is the same for both sides. So if you write along path 2, so here is the z direction, here is the y direction, and if you go this way and this way, you have dp dz times delta z in this direction, and then dp dy times delta y in this direction. So to go from here to here, you go dp dz delta z, small enough deltas, dp dy delta y, and you come from this side, you say dp dy delta y plus dp dz delta z along path 1. Both have to be the same because the pressure across the line is the same. What does that give you? You can write tan gamma as dz dy. dz dy is tan of this angle gamma. So you have dp1 dy. You can write those from here. You can write delta z, right, as let's say this is dp2 dz, dp2 dy, and this is dp1 dy, dp1 dz. So you can take the difference and write delta z and delta y as dp1 dy minus dp2 dy divided by g times rho 1 minus rho 2. Okay, so we used our hydrostatic relation as well. So the theory following Margules basically combines then with geostrophy. So same thing, we are sticking to geostrophy and hydrostatic balance, okay, and no friction. So in that case, u2 minus u1 can be written as g prime tan gamma over 2 omega, where omega is the rotation rate. So Margules had actually derived this for a front in the atmosphere. What is the jump in the winds across the front based on the slope of the front and the rotation rate? Okay, so that's our favorite reduced gravity. So g prime here is g delta rho over rho 1, so it is rho 2 minus rho 1 divided by rho 1. So we are just, or rho 1 minus rho 2 divided by rho 1. So we are just converting this into g delta rho over rho, and we are converting this into geostrophic relation. Okay, so u2 minus u1, both sides are geostrophic, so you have that in terms of the reduced gravity, tan gamma over 2 omega. Why does reduced gravity always show up? Because the gravitational pull on the water parcels is actually going to depend on the density difference between the lighter water and the heavier water. It's not absolute gravity. So if you drop the ball, it's just feeling the gravity on it. But if it is in water, for example, the density difference is then much smaller than the density of the water, and buoyancy of the ball becomes important as opposed to air. The density of air is much smaller than the density of the ball, so there you can ignore the difference, but here you cannot ignore the difference. So that is Margules' relation. It's a very simple thing we went through, but we will not be using it directly much, but nonetheless it's worth going through this adjustment problem in the lab, because we'll see that this in the real world has phenomenal significance. It's very important to understand this adjustment of stratification and rotation. Okay, that's what determines the atmospheric structure, atmospheric flows, scale of eddies. Many things evolve out of this tussle between rotation and stratification. Stratification basically means gravitational pull and buoyancy, right? If gravity is trying to pull you, why don't you just collapse? Because rotation can balance gravitational pull, which is what happened here. The heavy salt water wanted to collapse by gravity, but rotation created this cone and this front. Okay?